any of these. A, B, little b, and you'll see I have dimension of length, of course, and the product is 2 pi. So therefore, big A, big B, and big C are reciprocal inverse length. That's what you got. Okay, so as an example then, if you have A, B, and C are orthogonal, in other words, you have a cubic unit cell, then the A, B, and C big reciprocal space are very simple. They are just proportional to it. Okay, it turns out very simply, A is proportional. So if you have a cubic unit cell, the reciprocal space is also a cubic unit cell. And A, B, and C are pointing in the same direction of the real space vector. But this is in general not the case. I should point this out because you have cross product here. A is in the direction of cross product of the other 2 vectors of real space. So you have to be a little bit careful. For cubic unit cell is very simple because it seems to be in the same direction, except the length of that vector have changed because it's 2 pi divided by the spatial vector. But in most cases they are not. So let me just give you what they look like if you have different unit cells. So here, for example, you have different unit cells. So let's look at these 2. You have face center cubic, for example. In reciprocal lattice, it become body center cubic. Okay, it becomes body center cubic. And similarly, if you have body center cubic, it becomes face center cubic in reciprocal space. So you have to be a little bit careful when you talk about. They don't necessarily, both the big A and the small a vector, they don't point necessarily, oftentimes they don't point in the same direction when you're talking about residual space. Okay? And how do you use it? Well, you use it, we were talking about diffraction phenomena, we use it very easily in terms of diffraction in this. And one of the mathematics or geometric construction, if you like, of diffraction phenomena is called a Ewald construction due to, so here is a Ewald construction. And the way you think about this is that, let's say you have reciprocal lattice here, so represented by this white dot. These are my reciprocal lattice. Just think of it as like your real space lattice, except this is in reciprocal space. And then you have wave scattering, right? So let's say you have some center point in here. And in order to have diffraction phenomena, your vector, your scattering vector must hit one of these points, right? If you hit one of these points, then you can draw a circle, because from here to here, that's the distance or the magnitude of your k vector. You draw a distance, draw a circle like this. And whenever you hit a point in your residual space, you get diffraction of that point. Okay? If you miss other point, or you miss all these other points, you will not have diffraction of that point. Okay? So that is the idea of diffraction, a graphical way of showing you how you get this. And the logic is very simple, because the logic is simply said that k must change to k pi, right? Because this is my incoming wave, that's my outgoing wave vectors. And they must change by a residual state lattice. And so if I hit one point and it might meet another point, the circle with the same radius ensure that I have same magnitude. I only changing in direction. So here I go from here to here, and this change in direction, the momentum transfer vector, is therefore must be g. This give me my residual space integer of g. So you can see g here is like 1, 2, 3 times whatever unit residual lattice in this direction. Okay, so this is an integral of my residual space lattice. So that corresponds to my diffraction phenomenon. Okay, so let me come back to this like this. So if you look at diffraction theorem on this, the set of residual space lattice G determine position of the X-ray refraction. So that's what we're talking about here. So K, which is my momentum transfer vector, must be my residual space lattice vector. In other words, it must be some integral number times my unit residual space vector that I have. So K must equal to G. So since I have, so in the past, this is my K pi, right? So here, my elastic scalar K squared must equal to K pi squared. K pi is equal to K plus big K, which is my momentum transfer. And I said that momentum transfer must be the same as my residual space vector, G here. I substitute this into here, okay? And then what you can do is that you do a little bit algebra, and you can show, it turns out that you can show that K times 1/2 G plus 1/2 G squared must equal 0. And that is in fact my diffraction condition. So if you don't like that, you can just cancel these two, you get this one as my diffraction condition. This kind of rule are not that important. I just want to make sure that people realize that there is a way, there's a connection between my K vector and my residual space vector. And there's some equation, you should be aware there's some equation that tell you at what point there will be a diffraction occur. And this control, this will tell you at which of this point will generate a diffraction from the event in the residual space. Okay. And another sort of difficult concept, I'm sort of introducing this solid state concept that some of you may or may not have seen, is the so-called Brillouin zone. Brillouin zone is a Wigner site primitive cell, so-called Wigner site. Wigner, of course, is a great solid state physicist. We come up with a lot of these ideas that we have. So I just want to introduce this to you because you may hear about Brillouin zone from time to time when you come across solid state chemists or solid state physicists, especially when they talk about electronic structure. And we'll come back to this when we talk about electronic structure. And so what is Brillouin zone is related to residual space. So Brillouin zone, first of all, when you talk about Brillouin zone, you automatically should think about residual space lattices. Okay, so a Brillouin zone is in residual space, and it corresponds to a space that is created by plane that is so-called perpendicular bisector of this residual space vector. Okay, and let me just explain how you get this. What do you mean by this? If you look at this one, for example, I draw these dots, and these dots are my residual space point, right? Because I generate, I'm in A, B, and C, big A, big B, and C. I'm in my residual space. It's just like real space, except you know, I have to use some transformation to get from real space to residual space, and my length is inverse length, right? So that's how I think about my lattice, this residual space lattice. Now a Brillouin zone is very simple. Is that you have this point, you pick any point, okay? So you pick this one here, and you say that okay, I'm gonna connect this point to my nearest neighbor. Okay, so I connect this to this, this to this, this to this. So all my nearest neighbor point, and then I take half of the spacing here and put a plane across here. So this is known as the perpendicular bisector. So this is my perpendicular bisector along this length. Excuse me. So if you do all that for the nearest neighbor, what you end up is this shaded area. You see, so this is half of this. This from here is half of this, and this from here is half of this. You carve out a little point in here, and this is just done in 2 dimensions. You can imagine that you have another dimension in 3 dimensions. You can create a volume like this. Here I create an area because I have 2 dimensions. So this volume or area is what I call a Brillouin zone, the first Brillouin zone. Okay, so just go to your nearest neighbor in residual space, take the bisector and